Good morning, folks. While we're waiting for everybody to arrive, let me point to a couple of papers that relate to what we talked about yesterday. And one is here on your right screen. It's under papers and growth mixture modeling, and it is that antidepressant trial analysis. This is data from New York, Columbia University. And it's a joint paper with Hendrix Brown from the Prevention Methodology Group, Statistics in Medicine last fall. So here we are trying to tease out drug effects in the presence of placebo response, making the point that perhaps half of those people who respond to treatment, an antidepressant, would have responded also under placebo, which is a pretty dramatic, provocative statement. But I was going to show you, we talked about causal inference, and I was going to show you a key reference that you may want to take a look at. This one, number 8. It is, let's see. Let's see where you go. There it is. Konstantin Frangakis in this building in Biostat, and Don Rubin at Harvard. Principal stratification in causal inference, biometrics. That's where he talks about principal strata being like observed covariates, and you want to compare people conditional on covariate, that is within covariate values, which translates to these principal strata are mixture latent classes. So translates to comparing individuals within their latent class. So principal strata are latent classes from mixture modeling. So that's the beginning of this principal stratification thinking in causal inference. That is an important topic. If I only knew how to go back after being here, I would be happy. Where should I click to go back? Oh, there maybe. No? Okay, I'll go out and I'll go in again then, the hard way. So, is everybody here? You're awake. So, the other thing I was going to point you to, there's another application of latent class analysis, factor analysis, and factor mixture analysis, the topics that we talked about Monday, which seems like oceans ago. And it is a paper that is actually categorized as a survival analysis example. So you might not have found it had I not now pointed it out to you. It's this one. This one, with a long list of authors. Applications of continuous time survival in latent variable models for the analysis of oncology, randomized clinical trials using Mplus. So this was a collaboration with a pharmaceutical company group at Eli Lilly, two of whom are here. So this was a task of analyzing quality of life or patient-reported outcomes and trying to figure out how those responses to those measurement instruments related to survival in cancer trials. A very interesting kind of topic. And the Mplus group was supplied with data to analyze, and we're going to continue our collaboration. And it led to some interesting latent variable modeling of the quality of life instruments, or the PROs, as it were, the patient-reported outcome instruments. And this had to do with lung cancer, so instruments related to that. And there we go through a whole sequence of these models. And you might want to read, it's a 65-page report, and you may want to read it and see if you get some ideas about how one can go about analyzing data and reporting data. And then we related that to continuous time survival Cox regression, non-proportional hazard modeling actually, in a novel way, where the development over time in the patient-reported outcomes was related to predicting the survival. So you have two processes going forward. It's sort of a parallel process type of analysis that we mentioned yesterday, except that only one of the processes is a growth process. The other is a survival process. And what's interesting about that paper is that all the inputs and outputs are sitting on the Mplus website here. And so you can see how it was done. And it actually led to improvement in Mplus from version 5.21 to version 6.
Is this not working?
This should be working.
Oh, I thought you weren't using it and that it was, I should get batteries for it.
Thank you. You're on the go, aren't you?
Never such a thoughtful wife.
Yes, really. And the green back arrow came up. All right. And who's on Mplus discussion? Let's see. Last day. That's good. Because we're here. Oh, you're all here, right? That's right. All right. So are you warmed up now? See, there are 2 more coming. I knew. 3. Okay. I think that's all I was going to say to entertain the crowd, so to speak. Let's see. Where are we? It's Wednesday, so it must be topic 9. Let's see. From beginning. All right. And you are now
Banked. So are we going to do general announcements, or are you just out there doing your show?
I forgot.
He forgot. He thought he was at a comedy show or something.
I'll hand over to...
Right. But anyway, today's the day we're being recorded, so I can't see you. But anyway.
Wait, Brianna is not in the control group.
She's not.
Room, rather. Oh, she is there.
Well,
okay.
How would we know?
So are we on,
can't
Brianna?
See. Ah.
All right.
Okay.
We're filmed.
All right. So anyway, just general announcements from Nick and his group. When you leave today, there will be a little tray in the back of the room, and please put your badges in the tray. Leave them there before you leave the building. And just general things like, for anybody who's here new, please don't go wandering around. It's not safe on the streets around these buildings. Have your lunch either in this building or the hospital. There's upstairs on the 2nd floor, and then on the 9th floor in this building, you can find lunch, and also in the hospital. And any other announcements like that?
I was going to ask you, I mean, we're talking about serious matters here. Is it okay to make jokes? Can we be funny?
I think we've already proved,
Can we be funny?
Why start now? Yeah. He's been training me on this, and I blew it. All right.
Credits go to Saturday Night Live.
All right, so we're not going to make it. I guess we have to keep our day jobs. But anyway, and then for each 1.5-hour segment, hold your questions to the end, and we'll take question and answer session. Sorry, Pink, you tried.
No, you're coming well.
Anyway, and then we'll probably be ending today around 3 or 3:30, and we'll have lunch at 12. Go ahead.
All right. So we're getting a little giddy by day 3, but and here's our table of contents. And you thought it was only 1 page? No, it's 2 pages. So you are now the guinea pigs for a brand new day. This has never been taught before, so we have no idea how it goes or how it flows. But there are 150 slides, which should mean that we should be ending around 3:30 today, with the usual blocks of 1.5 hours and 15 minutes questions. And we're excited about being able to talk about this. This is all matters that are made possible by version 6 that came out in April. And that version is particularly focused on offering Bayesian features in Mplus. And we're going to talk through some basic notions of Bayesian estimation. And then we're going to go through a series of examples, path analysis with indirect effects, some mediational models. And we're going to move to factor analysis, but first cover model fit assessments that we need for factor analysis. And we're going to point out why Bayes is so great to have, because we have difficulty sometimes with maximum likelihood being slow or impossible because of these pesky numerical integration dimensions that we talked about at the end of yesterday. And then we're going to go on to talk about growth modeling applications, mixture modeling applications, and then focus on multi-level modeling towards around lunchtime, before and a little bit after, I think. And that is, despite the fact that multi-level modeling really is topics 7 and 8 in our course sequence. So in the sense, that's why we call this topic 9. It follows nicely after topic 8, when we have covered regular maximum likelihood multi-level modeling. But we want to give you this opportunity to learn about all of the base features now, since it's available in Mplus. And many of you already have taken topics 7 and 8 and would know what those topics contain. And in any case, you have a video of topics 7 and 8 on our website. And then in the afternoon, in last block, we're going to talk about missing data and the fact that Mplus version 6 now can do multi-imputations of missing data, so you don't have to go outside of Mplus to do that. And we're going to talk about how one uses that in various interesting settings. So we'll go straight to the ideas here behind the introduction of Bayesian analysis. And actually, Mplus has been a so-called frequentist program so far, up to and including version 5. Frequentist meaning that we do estimation by estimators such as maximum likelihood or weighted least squares. But actually, right from the start, Mplus was envisioned as a Bayesian program as well. In fact, when we got the SBIR from the Small Business Innovation Research contract from NIAAA in around 1995 or so, we hired 3 programmers, 1 interface programmer, 1 frequentist, maximum likelihood, etc. programmer, and 1 Bayesian programmer. So we had the idea that Bayesian analysis was important. Now, there was not a good match between the job and the programmer who was Bayesian, so he left. And we got so busy doing frequentist stuff for the last 15 years or so that we didn't really have time to go and finish up the Bayesian work we had started. But in the last year or year and a half, our frequentist programmer, Tihamer Asparojo, was encouraged to get into Bayesian analysis, and we now are starting along that path. So actually, I was doing work on Bayesian analysis in 1995 and have 2 papers on it. One that's published with Gerhard Arminger, and another one that is just sitting on my computer and was never submitted, but could be, I guess. Anyway, Bayesian analysis, why should one worry about that? Well, it really is something that's used almost as often as frequentist analysis in statistics. If you look at statistical journals, if you look at topics at conferences, biometrics, or the joint statistical meetings, I would estimate that about 40% are Bayesian analyses. Bayesian analysis papers rather than maximum likelihood or weighted least squares papers. And I think it's growing too. But there's much less use of Bayesian analysis outside of statistics. And I think that's unfortunate. And that's the sort of philosophy that Mplus builds on, trying to take good ideas from statistics and bring it into applied fields, substantive areas outside of statistics. And I think one of the reasons that it hasn't spread outside statistics in large amounts is that it's hard to do Bayesian analysis in existing software. There has been several programs doing Bayesian analysis. It's been created by, for instance, the British group around the bugs, BUGS, Bayesian analysis using the Gibbs sampler, which turned into WinBugs, which is probably the most popular software right now for Bayesian analysis. But I wouldn't say that that's easily accessible. It's a very good program, very general, but it's more geared towards the PhD statistician than, say, the psychologist who wants to analyze his or her data correctly. So if you look at the input from a bugs run, it looks techy, and it is. but it's extremely flexible. It's something that PhD statisticians should learn in their graduate programs. But I think we need one step of simplification, and that's what we have, the Mplus team has tried to do to make Bayesian analysis easily accessible, about as easily accessible as any other estimator in Mplus. So we'll see how you react to that now. And for Mplus, it also has the advantage, as the last bullet says, that it provides a platform for further development, because much of statistics now is done via Bayesian analysis. So there are certain things that, certain types of analysis that cannot easily be done, say, by maximum likelihood. And to be able to provide those kinds of interesting analysis possibilities to you, we needed to be able to work with Bayes to have that possibility and have Bayes included. So why now do we have to learn yet another thing? Why couldn't we have stopped at 8 topics? Why do we have to go to 9 topics? Shouldn't we have 10 to make it even? She says no. So why do we have to learn about Bayes? We have to motivate you on slide 5 already in the morning here, so you hang in there. Well, first of all, much more can be learned about parameter estimates and model fit. For instance, just a simple example, you will not only know about your parameter estimate and its standard error, you will get a whole distribution showing information about the parameter that you wanted to estimate, a whole distribution. And very importantly, we have better small sample performance. Very often in applied studies, we work with rather small samples. And maximum likelihood is a large sample estimator. It builds on large sample theory. For instance, it's only under large sample theory that the parameter estimates are normally distributed, and only then that a symmetric confidence interval is relevant. In practice, the small samples or other reasons may make the distribution not normal for the estimator, for the parameter estimate, and the large sample theory would not be applicable. So if you have small samples, you are helped by Bayesian analysis. And also, if you don't care about Bayes at all, if you don't even believe in the tenets of Bayes, although we will convince you very convincingly towards the end here, you can just think of it as a computational device. I mean, that's a heresy for those who are Bayesian. But you can be a latent maximum likelihood person using Bayes, shamefully, of course. But still, you can do analysis that couldn't be done by ML. Again, taking the example of numerical integration at the end of yesterday, when you have many dimensions of integration, and we will show you examples with 6 dimensions, 8 dimensions, 16, and even 80 dimensions in very down-to-earth, relevant, realistic examples, which would be impossible by ML, but are possible and have been done in Bayesian analysis in Mplus version 6. And new models can be analyzed. One interesting model, for instance, that's typically done, I have only seen it done by Bayesian analysis, is a change point analysis. For those of you who've gone through topics 3 and 4, we talked about change point analysis as a related to piecewise modeling. For piecewise modeling, you'd have a growth model that's at some point changes growth shape. For instance, pre-intervention development is different from development after the intervention. Piecewise modeling, you have to know where the pieces join, and that point has to be the same for everyone. And in some applications, neither of those 2 assumptions are fulfilled. For instance, you don't know when the prostate-specific antigens start shooting up exponentially. You don't know the point, and the point varies across individuals. So you estimate the change point, and that's typically done in Bayesian analysis, just to give you one example. There are many others. Now, we have several writings about Bayes here. already on our website because we figured we better be quickly put some helpful writings out there so you can know how to work with the program. So we have the technical appendix that Tiamer and I put together, which shows the technical implementation. And that's for the techies among you. And then a little bit more applied, the second paper, Bayesian analysis of latent variable models, going through several kinds of latent variable models and talking about why one would be interested in Bayes and what the things to look out for are, and some other general advice. And this actually all of these are being revised, the new versions put up continuously, it seems. So you should always make sure you have the latest version. Which reminds me, before I go on, how many of you check Mplus website at least once a month? All right. How many of you check Mplus discussion relatively often? All right, so you're on there. Anyway, and a recent addition is the multiple imputation paper, which shows you how to do that and how not to do that. And then my early attempt, or first attempt at trying to say this in simple ways, some of which have made it into this today's handout. So a brief introduction. And ongoing writing is on its way. Linda and I are finishing a first book, which is on topic 1. That is factor analysis and structural equation modeling, but one of the last chapters includes Bayesian analysis, and just to put the latest ideas out there into the book, because it applies to things like factor analysis and path analysis. And there are some novel features there, new types of analysis that we will show you tidbits of today. So this pedagogical writing will make it into a bigger context shortly. Now, let's give you some overview here. Let's go to 8 and 9. So we will be able to do Bayesian estimation in Mplus for for all of these single-level, multi-level, and mixture models. So when you say single-level models, it just means path analysis, factor analysis, structural equation modeling, mixture modeling, but not level fashion, but rather in a single-level fashion as the way we have done it so far. That is, we have not in these 2 days, Monday, Tuesday, used type equals 2 level. So when you don't have type equals 2 level, that's what I mean by single-level analysis. But the Bayes estimation is also available for multi-level models, and we'll see examples of that. And it's available to... I'm facing in and out here of my...
I think it's because when you stand in the corner.
I see, okay. And I don't have to stand in the corner? I'll stand here instead. And mixture models as well. And we cover continuous outcomes as well as categorical outcomes with probit link. And we are able to offer, and some of these terms now will not mean much to you until we define them, but we're going to work with so-called non-informative priors as the default, but also offer user-specified informative priors through the new model priors command. We're going to be able to work with multiple chains using parallel processing, quick computations. We're going to assess convergence with so-called Gelman-Rubin potential scale reduction factors. We're going to learn a lot of new interesting terms. We're going to look at posterior distributions, and we're going to look at their means, medians, and modes, and credibility intervals. We're going to look at various kinds of plots, trace plots, autocorrelation plots, and posterior predictive checking plots. All of that is available, including then also as a byproduct of this Bayesian development. It is really a byproduct, but an important one, namely multiple imputation of missing data, called data imputation. This is the Mplus term. Carried out using Bayesian estimation to create several data sets where missing values have been imputed. And the multiple imputation data sets can be used for subsequent model estimation using, say, maximum likelihood or weighted least squares. And the imputed data sets can be saved for subsequent analysis, or they can be carried out in the same run. So in one single run, you can impute the missing data and do the analysis. And we'll give examples of that, like I said, after lunch. Imputations can be done based on an unrestricted model using 3 different algorithms that we'll talk about. But what's an interesting, specific, and special, unique feature of Mplus is that imputation can be done based on a H0 model. That is, a specific model that you believe in can be used to generate the data, and that is advantageous in some settings. And what's interesting with multiple imputation, as we'll talk about after lunch, is that the set of variables used in the imputation of the data don't have to be the same as the set of variables used in analysis. So you can have more variables in your imputation phase than you have in your analysis phase. And single-level and multi-level data imputation is available, and multiple imputed data. If you have several data sets, say 5 different data sets, imputed data, they can be read using type equals imputation in the data command, which we had already in version 5, but there are some extra features to that now. Connected with this is something called plausible values, which is interesting. And we'll talk about that in detail this afternoon. But I'll just mention that it's frequently used in item response theory context, including ETS's National Assessment of Educational Progress, the nation's report card. So it is actually then multiple imputations for missing values corresponding to a latent variable. So everybody in the sample has missing data on the latent variable, right? So that's a special case of extreme missingness. And it has certain advantage to draw plausible values. It's like it has to do with factor scores, but it's better than factor scores. And we're going to tell you why it's better than factor scores. It's available for continuous and categorical latent variables. So not only factor scores for continuous factors, but you can also draw the category latent class memberships for an individual. And of course, you could do this also for random effects, which are just continuous latent variables. Like I said, it's more informative than only an estimated factor score, and we'll tell you why. And we have examples of that in the new Chapter 11. Chapter 11 of the version 6 User's Guide is a newly written chapter, so every chapter thereafter has a higher value, higher number. Now, this is an ongoing project, this Bayesian implementation in Mplus, because it is a huge topic, and we had to say, okay, this is it. We have to come up with version 6 and then add to it. So here is what's on our agenda for the near future. These are the features that are implemented. I guess this is the dead zone. Not yet implemented, and they include exploratory factor analysis and exploratory structural equation modeling, where Bayes can play important roles. We don't yet have loaded link, and we don't cover censored count and nominal variables yet. We do not allow for interactions between latent variables. We don't handle sample weights. Actually, sampling weights in a Bayesian context is a rare bird. I'm not sure about the research in that area, if it exists to any large extent. Let's see. We don't yet have C on X in mixtures. We don't have mixture models with more than one categorical latent variable. We don't have 2-level mixtures where you can have, as we will talk about in topic 7, we don't allow for a latent class variable on the between level. We don't have model indirect, but you can handle that by model constraint using new parameters, but that's the only model constraint you can do so far. And we don't have model test yet. But typically with Mplus, it moves forward quickly, so you will see several of these features in forthcoming versions, and that you don't have to wait for version 7, but it will be version 6.1 at some point. So now let's talk about the basics of Bayesian analysis, and I'll keep talking until we get to an application, and that will be an application in path analysis that Linda will go through. So now let's slow down a little bit and ponder this topic. So we have this slide 14 where we talk about the prior, the likelihood, and the posterior. And the frequentist view, and when we say frequentist, this is the statistician's term, to distinguish between frequentist and Bayesian views. They're so different. I mean, your statisticians almost fight if they're from different camps. And there are two camps in almost every stat department. The frequentist view is the way we have handled things so far. Parameters are fixed, unless you talk about random effects. But generally speaking, parameters are fixed quantities that have only one value in the population. So maximum likelihood estimates give you, for instance, maximum likelihood estimation assumes that you estimate a fixed parameter, alpha or beta, say. And that the estimates have an asymptotically normal distribution. So if the sample is large enough, and you keep drawing samples repeatedly and doing that estimation, that estimate will have a normal distribution over repeated samples. And that's because it has a normal distribution. You create your confidence interval as 1.96 times the standard error plus minus in a symmetric interval. Symmetric would be relevant because you have a normal distribution for the parameter. But the Bayesian view is that the parameters are variables, not fixed quantities, and they have a prior distribution. A prior distribution, we're going to talk about it, but it essentially means that you, the researcher, have prior beliefs about what likely values of that parameter might be. So the parameter is not seen as one quantity, but rather as having a distribution of likely values. And if you turn to the estimates of the parameters, they have a possibly non-normal posterior distribution. We're going to talk about priors and posteriors. It does not depend on large sample theory, which is a big advantage. The theory does not kick in because of large samples. And we're going to talk about diffuse or non-informative priors versus informative priors. We're going to see examples of both here today. So the way you can think of this is the progression from, if you have a parameter on the x-axis here, you have then, before you start your study, before you collect your data, you have a prior notion of where that parameter value will lie. It's probably close to the mean here of the prior, but you wouldn't be surprised if it's a little bit less or a little bit larger than the mean. This is your prior notion, and I'll tell you how you get the prior notions in a second. Then you collect your data. The data is represented by the likelihood of the data here. And the likelihood, think maximum likelihood, would tell you that the parameter estimate is over here, that is at the peak of the likelihood. But the Bayesian analysis would tell you that the estimate is here at the peak of the posterior. The Bayesian estimate is here because the posterior weighs together the evidence from the data with your prior notion. So you bring in information not only from the data, but from your prior notion. And the estimate, the Bayesian estimate here in the middle, will be a compromise of the two. And the way it's drawn here now, this is an informative prior. How would I draw it if it was a non-informative prior? Well, I would draw it with a very large variance. So this would be, the prior would be very flat and stretching very long across the x-axis here. And that kind of a prior would not alter the the likelihood very much at all, if at all. So essentially, with non-informative priors, you have a large prior variance, and the maximum likelihood estimate and the Bayesian estimates are very similar. They're going to be very similar with non-informative priors. Now, let's say a little bit more about priors then. And let's do it in terms of one of the few technical pages here. And to do that, we're going to get back to that Bayes theorem that we touched on yesterday when we talked about posterior probabilities in maximum likelihood estimation. But now we're talking about Bayesian estimation. So let's go back to our Stat 101 and talk about probabilities of two events, of an event A happening and an event B happening. You can think about throwing dice or picking balls out of an urn, as they tend to do. And we're going to distinguish between the joint probability of both events and a conditional probability, A given B, and a marginal probability of B. So here you see that the joint probability is a product of the conditional and the marginal. And we used that a lot yesterday. For instance, PB was the factor distribution, PA given B was the distribution of the factor indicators or latent class indicators given the factor. Now you may want to fill in here a second step, a second equality. Say equality equal P of B given A, P of B given A times P of A. That's also the same up there to the right. So now you're supposed to scribble. Why aren't you scribbling? Okay. Because then you would, as Linda pointed out, much more easily see why Bayes' theorem comes about. So Bayes' theorem says that the probability of B given A is equal to probability of A given B times probability of B divided by P of A. And you will see that eminently clearly from what you scribble up there, if you think about it for a second. Or the way I look at it, I just check that this is right by multiplying PA up on the left. Then it's PB times PB given A times P of A. That means it's the joint distribution of A and B. And what's on the right is then also the joint distribution of A and B. So the equality holds. So anyway, Bayes' theorem, was easy to get named for contributions in the 1700s. There weren't that many. So it seems like simple calculations, but it was a radical thought that this cleric from the UK had. And he actually used this idea as very powerfully, and it was the basis for the Bayesian analysis. How does that relate to anything, you may ask? And the answer is that when you apply it to modeling, you get back to what you have on the left screen. So you have a parameters given data, we say here. This you want to say is the posterior. So think of this as the distribution of the parameters, the brackets that I put, is sort of the distribution of parameters given data. Circle this and say this is your posterior. So if you identify things, it must be that B is parameters, A is data, right? If you look at this formula. So B is parameters, A is data. So what do we have on the right? Well, A is data, so it must be data given parameters times parameters, which was B, divided by data. So you use the Bayes theorem and get from left to right here. So we're saying that the posterior is equal to this expression here. And data given parameters, that expression is the likelihood, because the likelihood expresses, to simplify matters, it's a rough simplification, but the likelihood is the probability of data, of having observed the data given certain parameter values. So this is the likelihood. And the distribution of the parameters, well, that is the prior that we're talking about on the left. And data is data. So what the statisticians then say that the posterior, this what you have on the left, is proportional to, this little sign here, is proportional to the likelihood times the prior, the numerator, whereas data doesn't contain parameters and is sort of just a scaling constant, so it's proportional to. So hence, you're saying that the posterior is the product of the likelihood and the prior, which is what we're looking at on the left. Posterior is some kind of combination of the prior and the likelihood, where the likelihood, again, is the data as a function, probability of the data as a function of the parameters. Function of the parameters makes it possible to maximize it, with respect to the parameters. And the prior was the parameters, and out comes the posterior using Bayes' theorem. It wasn't too bad, right? So now, this is like, where do babies come from? Well, you should really have a true Bayesian here to answer that. I'm sort of learning to become a Bayesian. I'm a new student of this. That is, I did look at the literature 15 years ago and have started to look at it more now, but I'm by no means an expert. So today is a day where you can really stump me with many questions that I can't answer. But the idea is that research is not a one-shot deal. It's a continuing, accumulative process where you accumulate knowledge. So hopefully you always have, at a given point, you have results from previous studies. And you have hypotheses based on substantive theory that come from your theory, but also are guided by previous studies, be it just a pilot study. So you have prior notions, prior beliefs, from which you can form a prior distribution as input to the analysis. And in fact, if you've done confirmatory factor analysis, you have used very strong prior beliefs already. So you're already a Bayesian, just didn't know about it. So you have, for instance, in CFA, confirmatory factor analysis, you often have the hypothesis of zero cross-loadings. That is, for instance, you're saying that a hyperactivity factor does not influence inattentiveness items. It influences hyperactivity items. So you have zero cross-loadings there. And so you're saying that certain factors do not influence certain variables. So the hallmark of CFA are those fixed zero loadings, cross-loadings we call them. And that means that you assume that you have a prior which has mean zero and variance zero. So you just have a spike here. That's what your CFA hypothesis says. Whereas I would argue that it's much more realistic to say that you have a little variation around that zero value, even if it's a very small variation. So your prior for that lambda, the cross-loading, could, for instance, be distributed as a normal variable with mean zero. It'll have mean zero, but a small variance. So this is a mean and variance here. So the variance can be very small, but give you a little bit of wiggle room around that exact zero. And there may be reasons that you have overlooked for it to not be exactly zero. So if you use this variance, then the standard deviation will be 0.1, right? And if you multiply that by 1.96 for the 95% limit, then you find that 95% of this prior distribution will lie between minus 0.2 and plus 0.2. 95%. So that's a fairly tight prior, right? And 0.2 is not a very large cross-loading. If you talk about standardized metric in EFA, typically we say that for substantively interesting loadings, they have to be 0.3. Here we don't even get up to 0.2, even in the 95% interval, which is fairly wide. This is an informative prior, but it's much less strict than an exact zero. So And it makes a big difference in the analysis, as Linda will show you after the coffee. And it may be a much better way to do CFA. Maybe we're looking at a new development here. Let's show another feature, illustrate the non-normal posterior idea that parameter estimates don't have to have a normal distribution. So what you have on your left screen here, very colorful, is output from Mplus for one of these small cross-loadings. So we're talking about the same thing, actually, as on the right screen. So you have a distribution, and you see it's clearly non-normal. It's skewed with a long tail to the left, and it has a little bump like this. It's from real data. And we see that the mean, I'm not going to even claim to know what colors there are, but the mean is minus 0.2, so the mean sits here, 207. It must be this one. The mean sits here. The median is here, a little bit to the right because it's a skewed distribution. And the mode, which is the peak of the posterior distribution, sits here. And you can report any of these as your estimates. We're going to report the median as a default. Median seems to be more relevant for skewed distributions. And we also give you the 95% intervals. 95% of the posterior distribution lies between these seemingly green vertical lines. And that will tell you then you want to look to see if that interval covers 0 or not. If it doesn't cover 0, you can claim that the estimate is, using frequentist language, significantly different from 0 or significantly larger than 0. But anyway, we're going to focus on these intervals, and in Bayesian analysis, they're not called confidence intervals, but they're called credibility intervals. But they're still CIs. Thank you. Take your time. Now, then you have the maximum likelihood 95% here, which is plus minus 1.96 standard error units away from the mean. So here are the dark black lines here, and you see that they are off a little bit. That confidence interval is moved to the right. So it's misplaced on this non-symmetric distribution. And in fact, then, instead of reporting the estimate and the standard error as you do maximum likelihood, you could report the whole distribution. If it's a particularly important parameter, just show the whole distribution. And you will see how likely it is that certain values are the true values, so to speak. You can see the whole distribution. Now, let's take a few moments while we still have energy to talk about how this translation of information from the prior and from the data, from the likelihood, gets used or gets used and gets translated into posterior. And really, the reason Bayes has become so popular in the last decade or two is that there have been enormous developments, successes in terms of algorithms. So Bayesian analysis used to be more of a theoretical interest where it relied for computations on very difficult integrations. Here, once again, integration is replaced by numerical analysis using a technique called Markov chain Monte Carlo, MCMC algorithms. So just let's look at this for a second and think of it from a principal point of view. So say that theta represents a vector of parameters, let's say this. Theta represents everything that's unknown to you. So parameters, latent variable values, and missing observations. And we want to divide that vector or set of unknown quantities into S sets. So let's say that we have a situation where we have no latent variables, no missing data. A typical division would be that we divide theta into two parts. Parameters that have a normal prior and parameters that don't have a normal prior. So parameters that have a normal prior would be intercepts, means, slopes. Parameters that don't have a normal prior would be variances. Variances are more chi-square distributed than normal, right? So it could be a division into means, intercepts, and slopes on the one hand, and variances on the other hand. The way you arrive at your final estimates is by iteration. Iterations just like in maximum likelihood, but here, by starting the chain here, you say that you have these different sets, divisions of the parameter space, and I minus 1 could be the starting values that are generated by some default mechanism inside of the program. And then you can actually express the distribution of parameter set 1 as a function of the other parameters. It's a conditional distribution, and that conditional distribution can be expressed explicitly in many cases, particularly when you have so-called conjugate priors. So a conjugate prior is a prior where, where you have normal prior and then the posterior becomes normal as well. So you can express that distribution, and what you do is you take a random draw of a theta 1 value from that conditional distribution. That's why it's called Monte Carlo, because it's random drawing of this theta 1. And then you do for theta 2, the second set, given the starting values and given the theta 1 value that you got in the first step here. And then you go through all of the sets in a first iteration. And then you go back up and do it for the second iteration, where these values on the right here come from the first iteration, and onwards and upwards. And very smart statisticians have then figured out that this actually converges in principle under certain assumptions, and it converges to the posterior distribution of the parameters given the data, which is exactly what we want. So actually we have a multivariate posterior distribution for all the parameters or all the unknown. What I've shown you on the left is a univariate, one of the univariates from that posterior distribution. So this is explicated a little bit more in this Asperohov-Mutén technical implementation paper. Now, when we go through the actual analysis, we have to then make sure that this process has converged and that the estimates are of good quality. And we do that through several kinds of output features in Mplus, which I will just list here, and then we're going to go through them one at a time. First, we have a trace plot. We're going to define certain words here. A trace plot is a graph of the value of a parameter at these different iterations. And we're going to talk about a burn-in phase, which is a phase of early iterations that are basically thrown away because they are not estimates of good quality. And the posterior distribution is created from the remaining iterations. So the last half of the iterations as a default in Mplus is used as a sample from the posterior distribution. We can take a look at an autocorrelation plot because we want correlations between parameter values at different iterations to be low, to have sort of independence of observations in this posterior sample. We're going to talk about the term mixing, where the MCMC chain should visit the full range of parameter values, sample from all areas of the parameter density. Some problems, some examples show poor mixing, so we don't get a good sample from the posterior distribution. And we got to focus on being able to tell if this iterative process has converged using different kinds of indices for that to make sure that the Markov chain Monte Carlo process has reached so-called stationarity. And we're going to do that using base graphs in Mplus, and you have a whole set of them there on your left screen, right screen. And here's the first one, the trace plot. Pretty, right? Yeah, you get all kinds of colors here. So on the x-axis, you have the iterations going from 1 up to 100. And on the y-axis, you have the parameter values. So as a default, we're going to work with 2 chains. There are going to be 2 iterations going forward simultaneously. And it's good to have a 2-processor machine because Mplus then divides the chains onto the processor so they are calculated in parallel computing that way. So one chain is in one color and the other chain is in the other color. And I'm not committing myself. And you see that the starting value is pretty far off from where the remaining of the iterations are up here. And the iterations to the left of this line are part of the burn-in phase that are thrown away. And instead, we only focus on the iterations after the burn-in as representing the posterior distribution. And what do I mean by representing the posterior distribution? Well, you're supposed to tilt your head like this and look at it here. So the mean is about here, and then it varies towards that tail and varies towards that tail. So you can sort of figure out what the posterior distribution will look like from that, right? And the posterior distribution is using all of those points from both chains to create this posterior distribution that you looked at for that particular parameter. An autocorrelation plot should show that the correlation is close to 0. This is a very good autocorrelation plot. And it says that the correlation between adjacent parameter estimates across iterations are close to 0. This is computed, I don't know if you know about autocorrelations, they can be computed with lag 1, lag 2, lag 3, etc. So this goes up to lag 30. So imagine that you create a correlation by taking theta for iteration 1 correlated with theta iteration 2, and then theta 2 with theta 3 with theta 4. That's lag 1. And you can do that with lag 2, etc. This is sort of time series descriptive statistics, thinking that autocorrelations come from. So that's a good plot, and good autocorrelation plot. And let's take another trace plot. This is from only 100 iterations. Usually you're going to get used to working with maybe 100,000 iterations. It's a brave new world. Here's a trace plot where you have about 2,000 iterations. So it gets a little bit more busy with the blue and the red chasing each other. But this looks like a good trace plot. That is, it doesn't seem to be problematic. And I'm going to show you a problematic one as a contrast. Here is an autocorrelation that is portrays a little bit worse situation, but still okay. That is, the correlation is fairly high, but drops off. It drops off the more you increase the lag. So you have then a possibility of actually not recording, not including in your posterior distribution every draw, every iteration, but you could do so-called thinning. You have the THIN option in Mplus, so you can skip iterations. For instance, you could take every 30th iteration, where the autocorrelation therefore is much lower. So that's a possibility to get more independent samples. Or at least you can experiment with that and see if that influences your parameter estimates. Here's a trace plot 3, the last one, and I'm just going to tell you then that there we have a problem. So even after the burn-in line, we're discarding everything to the left, we have a systematic movement up and down here. A systematic movement up and down. And here's actually the autocorrelation plot corresponding to that. That when you have this movement up and down like that, it says that when you start getting a positive value, a higher value, you typically continue to get higher values. When you start getting a lower value, you continue to get a lower value. So the draws, the iterations are correlated highly across time. And that those two plots illustrate poor mixing. So that can happen for certain models, and it can happen for certain parameterizations. Whereas this trace plot doesn't have that up and down feature, so you can see how trace plot 2 looks a lot better than trace plot 3 in that sense. So trace plot 3 is a warning signal. It comes from real data that I encountered. I think it was for a categorical outcome analysis that was a little tricky. So here then, is the display of what we're really interested in, namely the posterior for the parameter. And you have it in, you can get it in two forms, histogram form, or a so-called kernel option, that where you smooth the histogram into a more continuous shape like this. It's the same picture, but shown two ways that you do in Mplus. And again, you see an example of a skewed distribution. It doesn't have the normal distribution for the parameter values as you would assume in maximum likelihood. Finally then, I think, we have the convergence checking, and it is quite intuitive. Here are the formulas, and you can totally ignore the formulas if you want to, but you can also read them through. What they boil down to is this expression, which is called, now you have a new term here, potential scale reduction factor, the PSR. And you will see that in the Mplus output. We were saying that we have as a default two chains of iterations going forward in getting parameter estimates, getting posterior, adding to the posterior distribution. So you can talk about a within chain variation of that parameter and a between chain variation. And you want to say then, of course, that convergence is reached when the between chain, the B variation, the between chain variation is ignorable relative to the within chain variation. So you want the between chain variation to be ignorable relative to the within chain variation of parameter values. So if you go back to your trace plot, you can see that that happens for, say, trace plot 1. The between chain variation is ignorable relative to the size of the within chain variation. And there's a theory behind why you should look at this particular expression, but it boils down to saying that you have most likely convergence if the PSR is not much larger than 1, of course. So when B is ignorable, it's 0, right? So you have W over W, so that turns out to be 1. And not much larger than 1 means less than, say, 1.05 or maybe 1.1 if you have many parameters. So Mplus will print that out on your screen. Here's another thing to watch on the screen. When you ask for that Tech 8, you see that you have a PSR going forward. And you have then, maybe we have a picture of it. Yeah, here it is. Here is the technical 8 output for base. And you have the iteration number. And you have the potential scale reduction factor going down. And you also get information about which parameter has the highest PSR value at a given iteration. So there can be particular parameters that are hard to nail down, hard to estimate. And that numbering corresponds to the Tech 1 numbering. And here you get the time for each iteration, which will then also tell you how long this is likely to take before converging. Actually, we could probably do a prediction based on that, how quickly the PSR goes down in the new version. So between and within variation, this comes out of Gelman and Rubin, and we have references in the back for that. Now, there's several options here then that are related to base, specific to base, and they're given on the user's guide pages shown there. I'm not going to talk about them right now, but instead, I'm going to leave the mic to Linda.
Thank you. Okay, so now we're going to take a look at a couple of examples of path analysis with indirect effects and look at the difference between what we will get using, for example, maximum likelihood estimation and what we'll get using Bayesian analysis. So this is from McKinnon's 2004 MBR paper, where he was interested in looking at the path model that's on the left screen. So there was a grouping, 2 different groups, and there was an intervention, so treatment and control, and it was aimed at increasing the perceived severity of using steroids among athletes. So, and it wanted to look at how the severity of using steroids was perceived, how in turn it increased good nutrition behaviors. So if they understood how bad it was to use steroids, would this increase their good nutrition behaviors? Now, there's a direct effect, of course, from the grouping variable to nutrition, and then an indirect effect via severity. So the indirect effect is the coefficient A times the coefficient B. So they wanted to estimate that indirect effect. So we'll leave the path diagram there. Now, let's take a look at how we would estimate that using Bayesian analysis. We know how we would do it using maximum likelihood. So in the analysis command, you have to say estimator equals Bayes. So it's really just an estimator choice. And we have also, we say processors equals 2 because we know that the default is 2 chains, and if we have 2 processors, 1 will be used per chain. So that if you do have that, that can increase computational time. So then let's see how we specify the model. We have severity on group, nutrition on severity, and then just the variance here of group. I'm sorry, nutrition on group also. So the reason we have this on 2 lines is because you can only have 1 label per line. So what else are we doing here? So we see the regressions that are set up, but we see that we have an A and a B corresponding to the regression coefficients of A and B on the left screen. When we want to use model constraint to estimate an indirect effect, we have to label the parameters in the model command. So by putting an A in parentheses, I'm labeling the regression coefficient for severity on group as A, and by putting a B in parentheses, I'm labeling the regression coefficient of nutrition on severity as B. So then down in the model constraint command, which is available for Bayesian analysis, but only using the new option. So we use the new option and we name the new parameter indirect. And then we say indirect is equal to A times B, with A times B being these coefficients. So we know an indirect effect is the product of the 2 coefficients involved. So that's all that we have to do to estimate this model. We're using we're not giving priors, we're using the non-informative diffuse priors, which are the default in Mplus in this situation. So I think it's pretty simple to set up and to use in Mplus. And let's see what we get. So the output looks different for the Bayesian analysis because we get different types of estimates. So in the first column, as always, we label the parameters using the Mplus language. So severity on group, nutrition on severity, nutrition on group, and the 2 intercepts. So in the first column is the parameter estimate. That doesn't change. In the second column is the standard deviation. And so what's it the standard deviation of? Bank told you that each parameter has a posterior distribution. So it's the standard deviation of the posterior distribution. And let me just move back also to say one thing about the estimate. The estimate can either be the mean, the median, or the mode. Now, the default in Mplus is the median. So what you see here, 0.282 is a median from the posterior distribution. The standard deviation is, of course, estimated using the mean. So that it's a normal standard deviation formula. Then we have a p-value. And just so I don't say it wrong, I'm going to read you what the p-value is. So the third column gives a one-tailed p-value based on the posterior distribution. For a positive estimate, so we have a positive estimate here. For a positive estimate, the p-value is the proportion of the posterior distribution that is below 0 or negative, so the proportion that's negative. For a negative estimate, so here we have a negative estimate, the p-value is the proportion of the posterior distribution that is above 0, so the proportion that's positive. So that's saying that if you have a positive estimate, you don't really expect to see any negative estimates. You would expect them all to be positive. So that proportion, so that's saying that 1% only of the estimates of the posterior distribution for severity on group were below 0. Okay, so that's that value. And you want these values to be small. Then, in the last two columns, you have your credibility intervals. So we don't call them confidence intervals, we call them credibility intervals. And if they, so let me just, I don't want to say this wrong. So if the interval does not cover 0, then the parameter estimate is going to be significant. So we can see here this does not cover 0. 0.095 is greater than 0. So severity on group is significant. Nutrition on severity is significant. Nutrition on group, so the direct effect, is not significant because this interval does cover 0. And anyway, this is how you would interpret this output. But the most important part that we want to look at, so let me put that up. Well, maybe we want to keep the picture, actually. So what's most important, though, is from model constraints. For those of you who haven't used model constraint, under new additional parameters are all the parameters given from model constraint. So the indirect effect has an estimate of 0.016, that's its median. The standard deviation of the posterior probability, or the posterior distribution, is 0.013 with a p-value of 0.01, so there were 1% negative values. And then we have a confidence interval that does not include 0, saying that 0.016 is significantly different from 0. So then we want to look at our technical 8 output and see what that shows us. So we have our chain. We showed 2 chains, and we show the seeds that they start from, and everything's randomly generated within Mplus as far as the seeds go. And if we had 2 processors, so each chain would be on a separate processor. And then we have our potential scale reduction, which we want to look at to see that it's close to 1 to indicate convergence. And then we show that we used only 100 iterations. So it only took 100 iterations to get to a convergence point. Let me go to 38 over here. So now here is the posterior distribution for the indirect effect. So we said that there is a posterior distribution for each parameter. So the one we're most interested in is the indirect effect, and here it is. It only took 100 iterations. And you can see here the mean, median, mode, and then we have the lower and upper credibility intervals are the green. And we can see that it's sort of hard to tell what this looks like. It converged so quickly in only 100 iterations that it's fairly sparse. So what we might want to do is actually Mplus, by default, Mplus figures out convergence on its own. But if you want to increase the number of iterations, you use the FB iteration option. But when you use this option, you specify that you want 10,000 iterations, for example. But when you specify it, Mplus is no longer going to be monitoring convergence for you, because Mplus already knows you can converge in 100. But if you want to see a posterior distribution with more than 100 iterations, then you're on your own to monitor the convergence. But you can see when we've increased the number of iterations, it gives us a much nicer posterior distribution to determine whether or not the parameter estimates are distributed normally or not. So you can see here that it's not normal. It has a long tail to the right. And you see, as I said, the median is what we use by default, but you can use the point option to select the mode or the mean. That's your choice. And Bengt, you're welcome to step in at any time, because this is the first time for us to do both of these. So we want to make sure we at least don't lead you astray. All right, so let's talk about this posterior distribution. So we have a mediated effect of the intervention, and the 95% Bayesian credibility interval does not include zero. So that means that it's significant, the indirect effect. In maximum likelihood, we don't find this. We do not find a significant indirect effect if we just estimate that model with estimator equals ML instead of estimator equals Bayes. However, what they did in the paper was they used bootstrap standard errors and confidence intervals with ML, and they found significance. So the non-symmetric confidence interval and ML was able to find the significant indirect effect. The traditional symmetric confidence intervals and ML were not able to find significance. So both Bayes and non-symmetric confidence intervals in ML found that significant effect. And as I said, this was from this paper, or no, that wasn't from that paper. The McKinnon paper 2004 was the indirect effect. Here's another example that we're going to look at. We're going to look at Yuan and McKinnon 2009, a Bayesian mediation analysis, where they actually used Bayesian analysis instead of ML with bootstrap standard errors. And Bengt has a note here, nice description of Bayesian analysis, so that sounds like a good paper to look at. And what they did is they used informative priors. So remember, in the Atlas example, we used the default diffuse priors. Now we're going to look at another indirect effect example, but we're going to use informative priors based on previous studies. And we'll talk about what the informative priors are when we look at the input. And when we do this, that 95% credibility interval shrinks by 16%. This was done by the Yuan and McKinnon using WinBugs. And their paper has the WinBugs code. And I'm going to show you the Mplus code. And the exact same results are obtained. So 42. All right. So here's the model command. So we have M on X, and we're calling it A, labeling it A, Y on M, and we're labeling that B. So the indirect effect is going to be A times B, and then Y on X, the direct effect. You can see we have estimator equals Bayes, processors equal 2, and FB iterations equals 10,000. We know now that that is going to converge very quickly, this model, so this type of model, so we're going to increase the number of iterations right away. And now here's what we're using new for this example. We're using model priors. So we're saying that the parameter labeled A is distributed normally with a mean of 0.35 and a variance of 0.04. So that's how you specify the priors. And there are many, many different types of priors. We're showing you normal, but there's about 6 different types, and the arguments in the parentheses differ based on the type of prior you're using. Here, the arguments in the parentheses are the mean and the variance. So parameter B is distributed normally with a mean of 0.1 and a variance of 0.01. So we're now using informative priors. And model constraint is identical to the last one that we looked at. Whoops. No, I guess that's all there is. You didn't do any results. Okay, now Bengt is back to discuss model fit. Although actually, we should take questions.
Yes, add something to that.
Here.
Thank you.
Should I back this up?
No, that's fine.
Oh, well.
Yep.
Okay.
Thanks. So this is an interesting situation where one can use information from previous studies to get a more precise answer for the current study. So it is a little bit like meta-analysis. That is, you have several studies. You don't go in blind to your new study. You actually draw on information from the previous study. In a way, you want to weigh together the information that you had in your last trial with the one that you have in this trial. So it has the meta-analysis flavor. The prior that we add here adds to the data, adds information to the data collected in this current study. Now, of course, there is the danger here that you see immediately, that a bad user would give the prior that would give him or her the results he or she wants. So don't do that. So that's all I wanted to say.
Okay. Okay, so that's cheating, and we don't cheat. All right, so let's take questions and answers, or questions, and we'll do the answers.
Yes, gentleman in the middle.
So related to slides 27 and 28, so you showed histograms and kernel density plots. Could I look at a cumulative distribution function for a parameter? And if not, is there a way to export these values into another program?
So the question is, could we present a cumulative distribution function plot, not in Mplus currently, but yes, you have the data that's used for the plot is available to you. So you can take those data and put them into a new program and do whatever you want with them. So for instance, you may want to import it to R and do various kinds of manipulations of plots.
What's the output or the?
It's called .gph.
So this is when you use the plot command, you automatically get this .gph file, and so you don't have to really ask for it. It's just there. But isn't there something else in the menu about results in the plot menu? Or is everything in the GPH file?
I think everything's in GPH
Okay.
file, yeah. Okay, more questions? Yes, Richard, in the VIP seat here.
But you mentioned if you...
He has a special box here.
If you ask for more than the default iterations, which I think is 1,000.
I'm sorry.
The default F iterations for Bayes in Mplus is 1,000 or 100?
No,
It's,
so go ahead.
No, I don't know what the default is. Is it 10? Is it 1,000? It must be in between
That-
100 and 10,000.
good inference. It is 50,000 iterations is the default. If you haven't,
I see.
if
Right.
the process hasn't converged as judged by that criterion, the PSR, it goes to 50,000 and stops.
So, if you ask for, you said, if you ask for 10,000, you're on your own.
Right.
Elaborate a little bit about what that means.
Yeah,
It's scary, like a precipice, and I'm wondering.
Well, it's
you're not
It's-
totally. Go ahead.
no, well, no. It's okay. Well, I'm just saying that once you use FB iterations, we don't check convergence anymore. So you need to check it yourself. And if that's scary, I'm sorry, but
No. Can I add to that? Mplus still prints out the PSR.
but you
So you
have
can see
yeah.
that from Tech 8. And what you will probably find, if you converge at 100 iterations and you say, now I want to look at 10,000 to have a smoother histogram, you will see that the PSR factor hovers across around 1 for all of those iterations between 100 and 10,000. And then you can be fairly confident that it is converged. But it's not Mplus telling you that, it's you telling you that.
You know, when you don't use FB iterations, Mplus goes on until it converges, or it doesn't converge and it says it didn't converge. But when you use FB iterations, we just say, Mplus just says, okay, you want 10,000, you get 10,000.
And F in FB, as you might guess, means fixed, and B means base. So that's the fixed base iterations. Then there's also the option of B iterations. And that just ups the default maximum of 50,000 to whatever you want. So you can say 100,000 instead, and then Mplus will stop somewhere before then.
If it converges. Yeah. It's not as scary, I guess, as
Yes.
it sounds.
Could we go to slide 25 and 26, please? Which is what I can imagine is not a typical finding, but certainly one that could come up. Could you give some guidance as to does this set of plots indicate lack of model fit, a bad model, bad informative information on priors? Or could you just give a little bit of guidance about what one would do, given that I saw this plot and this set of plots? What would be next steps?
Right, okay, so the question is, what does this plot mean and what do you do about it? No idea. No, you can conclude from this plot that you're working with an analysis that has a difficult model. So it's a difficult model for the data. And typically it says that your parameterization, you can parameterize things differently. For instance, just a simple thing like in factor analysis, you could set the metric by fixing the first lambda loading to 1, or you can fix the factor variance to 1. In base, that makes a little bit of a difference in certain situations, just as a very simple example of parameterization. So, so you can depend on the model and depend on the parameterization, and it also could show that this algorithm is not effective enough for the combination of model and parameterization. So what you do with this, you would probably, the first thing you would do is choose a much longer chain, increase the number of iterations, FB iter or B iter, and you may also do thinning, that is, you may skip over some iterations, and you experiment with that to see if the parameter estimates change in any meaningful, important way. That's how you would go about it. All right. Yes?
I have two questions. The first pertains to slide 35, the interpretability of your test of significance. I suspect you can use the same words, but in a Bayesian context, I suspect the meaning is going to be a bit different. For example, if we say that something is statistically significant at the 0.05 level, what we're really saying is probability of type 1 error is below 0.05 with regards to the null hypothesis. But we're doing something a little bit different here, right? I mean, you're going to use the same words, but I suspect it in this context means something a little bit different.
So we come from the frequentist area, so we will slip into frequentist language quite often. A Bayesian would not say that this estimate is significantly different from 0. I think a Bayesian will just, let's see, we have focus on this. A Bayesian will just say that the credibility interval is this, and since it doesn't cover 0, we believe that the parameter value is greater than 0.
Okay, good.
We would stop there, I think.
All right, yeah, I think that's important.
And if we have several books that we will refer you to at the end, and they will make clear how you should use that kind of different language. But you don't test significantly different from 0. You don't have that language. Although we will probably slip into that many times.
Got it. And my follow-up question is a more general one, and that is, with the priors, one would think, and I'm going off your comment about the meta-analysis, that as we learn more in a particular literature about a problem, we would expect the priors to become more informative over time. Is that correct?
Smaller and smaller variance,
Yeah,
yes.
okay, good.
Right. With
That's a very positive, yeah.
the more you study something, the more you know about it. So you should have a more informed.
In fact, we had wanted to have a meta-analysis example in here, but this is like teaching mixture modeling 10 years ago, when we had relatively few real examples because they hadn't come into us yet.
Right.
Catch us 10 years from now, and we will still be talking about.
Exactly.
Yeah,
We'll be up here with our walkers.
Okay, we have a question here.
I just want to know if when you're you're specifying your iterations, should you double it because then you can use the second half? Is it always going to only use half of the iterations you specify, or are you specifying the number you actually want to use after that same amount of burn-in?
So this is
the total.
That's the total.
Well, when you say 1,000 iterations, 500 are burn-in.
500 are burn-in, but then you have two chains, so the 5 would be 500 plus 500 for the posterior. There is not in Mplus. I think implicit in your question is there a way to say in Mplus how many burn-ins you want? And there isn't currently. We just discard the first half for simplicity.
No matter what.
No
So you
matter what.
specify whatever you want.
Yeah.
In your estimate to be based on.
Yeah, right. Go back from that. Yes.
How's the prior get weighted with the current data? Is that, I thought the fault was it weights them equally, but I guess is the weighting based on the variance of your prior, basically?
Oh yeah. Yes, the variance of the prior. How does the prior information get weighted with the data? I could say it like that. Yeah, if the variance is small, the prior has more weight in the calculations. If the variance is very large, eventually it has no effect at all. And you will essentially get the same estimates as you get in the maximum likelihood, in case you could compute the maximum likelihood. More questions? Yes, lady in the middle back.
Yes, so this was a relatively simple path model with not too many variables.
Yeah.
And your focal parameter estimate of interest was the indirect effect, so you had few priors that you specified in the model. Suppose you had a more complex path model, more variables. Would there be costs and benefits to using informative priors for certain parameters versus diffuse in a model?
So the question is if you have a more complicated path analysis with more variables and more pathways for your direct effects. I don't think that's a complication even when staying with the default non-informative priors. I've been using it now for a while with quite large problems and many parameters. I think just before we left, I worked on a model with 250 parameters, and it works fine.
And to follow up on that, would using informative priors for some parameters and not for others have spreading effects at all on the estimates with the diffuse priors?
yeah, okay, so that question is, if you have informative prior for certain parameters and diffuse priors for others, will the informative priors for those parameters influence the estimates for the others? And no, I think not. I think not. And Linda will show you an example where she has informative priors for only some parameters. And actually then, we have the data on our website and you can go and check how much it changed the other parameters, but I don't think much or anything at all. More questions? You're almost at the coffee. Yes?
So starting with slide 37 and then looking at the distribution in the next few slides after it, I'm curious that in 100 iterations it said it converged, and then we got the histogram and we get the mean. And then once we did it, we decided we're going to look at, if we want to better look at the posterior distribution, we're going to do more iterations, and we got a slightly different result, particularly for the mode. I was just curious that you know, the PSR says we've converged, but doing more iterations, we've got an obviously better distribution. So it seems, you know, should we trust the PSR? Should we kind of look to see, make sure, what is it? Are we actually filling out our distribution?
Yeah, it's a good question. It reminds me that I should say something more about that. My experience is that even when the process has converged in terms of PSR, you are wise to go beyond that. By say if it converges in 1,000, you may want to go up to 10,000. Because what can happen, and this has been a long debate in statistics, should you do several chains or should you do one very long chain? Big debates, passionate, statisticians become really passionate about it. And I found that sometimes even when it converged at 1,000, it can then, the PSR factor comes down to 1 at 1,000, it can go up a little bit again, and then come down, and then it stays down seemingly forever, 10,000 iterations. So I go a little bit beyond to make sure. That's one point. The other point is that with Bayes, you're not going to get exactly the same estimate to 3 decimals as we're used to for maximum likelihood. You know, maximum likelihood has that very precise definition of convergence. The derivative of the likelihood is exactly 0 to 6 decimals or something like that in Mplus. And you don't have that here. But what is probably very similar here between the 100 iterations and 10,000 is that the median is probably very similar. And the results, your conclusions would not be different. And the difference between the 10,000 iteration run and the 20,000 iteration run will be even less. So we don't get exact to the decimals, but we get very close results. It doesn't have any practical drawback to it, that they differ a little bit. Yes?
In the calculation of PSR, do we use the burn-in samples also?
Calculation of the PSR does not use the burn-in sample, no. It uses only the variation after that vertical line.
I think the burn-ins aren't used for anything, right?
No.
They're discarded and not used.
Yes.
Okay.
With regards to this is a follow-up question that was asked earlier on slide 15 of the weighting of the priors versus the likelihood function. So greater weight to the prior, the smaller the variance. And then I suspect for the likelihood function, what, the larger your sample?
Yes.
Okay.
Yeah. So the likelihood wins by, the likelihood dominates when it has a lot of people in it. And when it has few people, the determination of the series is more determined by the prior.
Okay, thanks.
Nick, you look like you want to say something.
No.
Do you want to come up on the stage? We're being videotaped.
I think Nick wants to say that he wants us to take a break. And we should probably do that and come back about 10:35.
I will say something, we're going to take a break.
Okay.
Yes, we are.
So thanks for reminding me, but I assume you guys have figured this out. That you can get cabs across the street at the hospital.
Oh, yeah.
If you're going to head right directly to the airport from here. And, you know, it's probably the easiest and closest way. A couple of folks have mentioned to me that they had trouble finding J's. So just as a recap, you know, I guess you would call it a restaurant, J's exit out of this hall, and then walk to the key in the